All right. Hey, everybody. Welcome back. So in this video, we are going to continue our progress of examining the derivative and proving results about the derivative that are familiar to us from calculus, but now we can rigorously examine and prove using the tools and tricks of real analysis. As we've seen in previous videos, we can define the derivative of a function at a point P by an appropriate limit of a difference quotient. And then we can prove facts about the derivative by looking at that difference quotient and proving facts about that, or about the limit of the difference quotient function. So in short, a lot of our results here in chapter 10 are referencing appropriate limit function results from chapter 6. And we'll see an example of that right here. On the table for us to prove is a fact that we all know and love that, in essence, says that the derivative of the sum of two functions, so the derivative of f plus g, is equal to the derivative of f plus the derivative of g. This is something that we use again and again and again in calculus and in classes beyond calculus. Let's try to rigorously prove this using our techniques from real analysis and sort of appropriate referencing of results in chapter 6. Before we get underway, I just want to explicitly point out that when I use this, what I'm saying here is essentially sort of two things, right? I'm saying that if a function f and g are, if functions f and g are differentiable at the point P, then first and foremost, the function f plus g is also differentiable at P. And then second, that I actually have a formula on how to compute that quantity. Now, just to remind you, right, this expression right here, the f plus g prime of P, this is representing a limit as x goes to P of some big difference quotient, right? As is, I should say, this expression and this expression over here, right? Every time we have one of these derivative, like f prime of P, g prime of P, or f plus g prime of P, that is shorthand to say the limit of this expression. That's how we're denoting the limit. So when I say that this function is differentiable and satisfies this, I'm really making these two claims. First, that the appropriate limit here actually exists. And second, that I actually have a nice formula for it. It will just equal whatever this limit was plus whatever this limit was. So with that in mind, let's get into it. The key, once again, will be referencing an appropriate result from chapter 6. And so let's start there. Okay, so this is the result from chapter 6 that we really want to hone in on, right? The algebra of limits. Now, as a reminder, this said that if I have two functions, f and g, and I can calculate the limit as x approaches P of f, and I can calculate the limit as x approaches P of g, and if both of these limits exist, then I can take the combined function that is those two being added together, so f plus g, and the limit of f plus g would equal the limit of f plus the limit of g. This is more or less exactly as it was written back in chapter 6. So the key observation that we want to make is that this is a expression involving limits, and this is secretly an expression involving limits, and we should be able to align this statement to this statement up here. However, I don't really want to be working in terms of f and g down here. Instead, I want to rephrase things so that it is involving these derivatives, and these derivatives were limits not of our function f and g, but of difference quotients involving our limits f and g. In other words, right, this expression, let's say f prime was really an expression involving the limit as x goes to P of not just f, but f of x minus f of P over x minus P, right? And similarly, this g over here, right, g prime of P was the exact same thing, limit as x goes to P, but that should be g of x minus g of P over x minus P. So taken together, I realize that what I really want to have down here when I'm referencing my algebra of limits is not an f right here, but rather the entire difference quotient f of x minus f of p over x minus p. Similarly, for g, I want to have g of x minus g of p over x minus p. And of course, that will also affect what we have over here. So this should be replaced with f of x minus f of p over x minus p. And then the g will again be g of x minus g of p over x minus p. Okay, so I think we have this all set up now the way that we want it to be. And now let's turn back to the theorem itself and recognize that this expression is secretly just this expression, but rewritten. And we'll see that here in just a moment. Okay, so here we are. We can see here that our starting point is to consider this expression right here. Keep in mind, we are trying to show that the function f plus g is differentiable at p, and that means that we really need to compute, if I want to give that an entire name, maybe this is overkill, but if I want to call this h, right, then to show that it's differentiable, to show that h is differentiable, I need to compute the limit as x goes to p of h of x minus h of p over x minus p. Right? So I need to show that that limit actually exists. So because h is just the function f plus g, this means that we are considering the limit of f plus g of x minus f plus g of p over x minus p. To proceed, we can remember that we defined f plus g of a quantity, so f plus g of x is just f of x plus g of x, and we have a similar result about f plus g of p. So this just can become rewritten, right, as we have f of x plus g of x, that was the first piece, minus f of p plus g of p, and I should have parentheses around that because that is all being subtracted. And then all of that is over x minus p. Okay, so all we've done is sort of parse out our notation, but now we want to rewrite this in a clever way. And specifically, we are going to group things in what is currently under a common denominator. We're going to split that into two fractions, specifically, as you might expect, with our f's taken together and our g's taken together. So this is really nothing more than the limit as x goes to p of, in the first expression, we have f of x minus f of p over x minus p minus, or rather plus, g of x minus g of p over x minus p. Right, so all we've done in going from that last equal sign to this equal sign is we have split up this fraction in a clever way into two fractions across this shared common denominator. And this is great because this is exactly what we have up here. So now, by the algebra of limits, right, by theorem 6.9, we can say that is going to equal, by theorem 6.9, that is going to equal the limit as x goes to p of f of x minus f of p over x minus p plus the limit as x goes to p of g of x minus g of p over x minus p. Right? So again, the algebra of limits here says that if each of these individual limits are known to exist, then the limit of this thing should just be that limit plus that limit. Luckily, we know that both of these exist because both f and g are differentiable. So because f and g are differentiable, this limit exists and it equals f prime, and this limit exists and it equals g prime. So we can conclude at last that the thing we were trying to compute actually equals f prime of p plus g prime of p. Yay, it's awesome. All right, so yeah, another fun example of proving something that we definitely knew is true because we've seen it in calculus, but now we really know that it's true because we've rigorously proven it using real analysis and by cleverly making use of the results we had in chapter 6. So thanks so much, everybody. Take care, and I'll see you next time.